Hello everyone and welcome back to the class of fundamentals of particle and fluid solid processing. We were in the transport of fluid solid systems and we had completed in the last class the slurry transport. Today we will see the fundamentals about the pneumatic transport. So pneumatic transport, as I mentioned earlier, when the fluid phase that carries this solid particle is the gaseous phase. So the transport of particulate solids in the presence of a gas is called the pneumatic transport or pneumatic conveying. Now these are widely applied in transporting a various range of particles, that is, say starting from wheat flour, wheat grain, plastic chips, or even coal. There are two categories or two types of this pneumatic transport depending on the solids loading or the solids concentration. One is like the slurry we had, it is the dilute or the lean suspension, and the other one is the dense phase transport. So in dilute or lean suspension, we require a large volume of air at a very high velocity. So like in slurry transport that we mentioned, that most widely used liquid was water. In this case, the gaseous phase is mainly air. So we will mostly talk as the gaseous phase as air in this section. Now in case of dilute phase, we require huge volume of air that would be required at a very high velocity to take these fine particles or the particulate solids from one place to the other. In case of dense phase transport, the particles are not fully suspended, or all the particles in fact are not in suspension. So but still, why this transport or this kind of transport we will be talking about, or why we will be studying? Because it was also widely applied till a certain period in the industry, and even in some cases it is used, although the particles are not fully suspended, but due to this low requirement of air volume, which in terms of the lower mechanical energy despite very high pressure requirement, it is beneficial in transporting the particles for say a shorter distance or even in a straight pipe. Why it is so, we will see that when we go into the details of the flow design. Now since here the velocities of the air that induces the movement of the particle is lower, that means it offers lower degradation of the pipeline network by attrition or the erosion. So these are the benefits we had in dense phase transport despite the particles are not fully suspended. Now if we go into the details of the dilute phase flow or the transport and the difference between the dense phase transport, these two are basically characterized by certain parameters or classified by certain parameters. This can be detected by looking at the gas velocities immediately. So this dilute phase flow can immediately be detected if there is a very high gas velocity, say above 20 meter per second, and slow solid concentrations, say below 1% by volume, as well as low pressure drop per unit length in the transport line. If we had these things in a certain working condition, we can detect that this is the dilute phase transport that is happening. And it is also applied in short route, okay, but in certain cases it is used for prolonged routes as well. In this case, since there is a very small concentration of solids present in the air, each particles behaves as individual particles. So, individual particle behavior dominates, as well as the fluid particle interactions that dictates the property of this flow. In the contrast, in dense phase flow, it can be immediately recognized by the low gas velocities in the range of 1 to 5 meter per second, high solids concentration, say more than 30% by volume, and high pressure drop per unit length of the transport line. In this case, as I mentioned earlier, that the particles are not fully suspended. I mean, all the particles are not fully suspended. In ideal case, or in one ideal scenario of the dense phase case, what would have been the whole cross section would be filled with the solid particles. But we can logically understand that that scenario can lead to choking of the flow. Now, since there are multiple particles in a close proximity in a denser manner, so there is a significant interaction between the particles, which cannot be neglected like that can be done in case of dilute phase transport. Now, there is no such clear distinction or clear guideline to distinguish between these two flow regimes, that is the dense phase and the dilute phase, but there are several attempts in order to characterize them or to classify them. One of such shows or dictates that we can look at these parameters that is listed here in order to differentiate the dense phase flow from the dilute phase flow. We can look at the solids to air mass flow rates or the ratio. We can look at the solids concentration in the flow. That this helps us in determining which would be the flow regime or which would be the characteristics of the flow. So, in dense phase flow, it should occupy the whole cross section of the flow at a certain time as the flow happens. In case of horizontal flow, the gas velocity would be insufficient in case of dense phase flow to support all the particles to remain in suspension. That means particle settling will happen in case of horizontal flow. Say horizontal pipe, the dense phase flow is happening. So, we can characterize that this is a dense phase flow if we see that the particle settling are happening, or say there is a saltation regime like we have seen in the case of slurry transport. In vertical motion, or when there is a vertical flow in the pipe network, this pneumatic transport is happening. In the dense phase flow, there will be the reverse flow of the solids. That means the gas phase is not able to withstand all the solid particles in the suspension. If the reverse flow of the solids happening, then we can take that this is a dense phase flow. So, these are the broad guideline by which we can differentiate between the dense phase and the dilute phase transport in the case of pneumatic conveying. Now, in the case of vertical transport, when it is say going against the gravity, now in such case the critical velocity where the operation should be maintained, we call that as a choking velocity, and in case of horizontal flow, that velocity we mention as saltation velocity. So, in horizontal case it is the saltation velocity, and in case of vertical flow we would mention these critical velocities at the choking velocity. Now, this is what is important, or this detection are what important in order to maintain the flow, because our goal is to transport the solids by this gaseous phase or the air. So, we have to know that what is the minimum air velocity that is required to have that, to achieve that. Now, that should be done with the as minimum air as possible, because then the energy cost, the energy requirement or the air requirement, everything is lower, and with the minimum amount of air the mean velocities would be lower. So, the abrasivity and all these things can be taken care of. So, if we look at the vertical transport in case of pneumatic conveying, say this line, this AB, where x axis is the superficial gas velocity and y axis is the pressure gradient. So, in case that this is the simple airflow is happening without any particle, then it would result in this line AB, where G stands for the solid's loading, or say the mass flow rate of the solid. So, here there is no solid in this case. So, this is basically the frictional resistance. Now, when we introduce solids, or say the dilute phase transport is happening, in this case for a certain solids concentration or the mass flow rate of the solids, we see that at very high velocity the concentration of the bed is lower, it is fully suspended, and the kind of say dilute phase transport is happening at a very high velocity. Now, as we go down or decrease the velocity, the frictional resistances becomes lower, the pressure drop becomes lower, but after a certain point the static head due to the solid particles becomes dominant and actually increases the pressure drop requirement. So, the pressure drop again increases. Now, at this point the gas velocity is basically not able to penetrate the solid bed, or say the solids are not being carried with the gas velocity that is provided. And if we further decrease that, this scenario would happen when the solids will completely block the channel and the flow would not be there. That velocity we call the choking velocity. Now, here we can see in the bed structure that there is a kind of bubble passing through the fluidized bed. This kind of scenario is happening that we have seen in case of fluidized bed, kind of a bubbling regime is there. Now, in this case there is a considerable fluctuations of the pressure that can be obtained through the vertical plane. So, it is basically the slugs of air that would be moving at an irregular time or the irregular interval. So, this velocity we call the choking velocity, and that means we have to operate the bed in this region or higher than this value, the choking velocity, but somehow near to this range there is some unstable condition of the flow behavior. So, it is better to operate a far distant from this choking velocity, because nearer to the choking velocity there is a transition zone, there is, say, it can move towards this choking velocity at any point of time. The control is very poor in that region. Now, if we increase the solids concentration in the feed, that means the solids loading, if we increase, what happens? This choking velocity also increases. The requirement of the velocity in order to choke, that also increases. So, that means the choking velocity can be arrived by two conditions. One is that if we fix the solids loading and decrease the velocity, we can arrive at choking velocity, or for a particular superficial gas velocity, if we increase the solids concentration, then also we can arrive at the choking velocity. So, that means once again, if we decrease from this dilute transport where the concentration is lower, and if we decrease the velocity, the superficial gas velocity, the bed concentration increases, and at a point it is not able to further withstand the height of this static head of the solid particles, and the pressure drop again increases, and after again critical limit it basically blocks the flow, and that is called the choking velocity. So, this pressure drop along the length basically dependent on certain factors, or it is a combination or the contribution from all these parameters, which are the pressure drop due to gas acceleration, the pressure drop due to particle acceleration, the gas to pipe friction that contributes to the pressure drop, solid to pipe friction, static head of the solids, and the static head of the gas. So, the combination of all these parameters contribute to the overall pressure drop across a length. Now, so which means prediction of choking velocity is important, but unfortunately there is no as such critical or say the theoretical development on the choking velocity. There are several experiments, several correlations have been proposed for choking velocities, and one of such is given here. So, where you see h is the choking velocity, epsilon Ch is the voidage at the choking velocity, G is the mass flux of the solids, which is mass flow rate MP divided by A, the cross sectional area for the flow. Ut is the free fall or the terminal velocity of a single particle in the gas, and we have to solve these two expressions simultaneously to get these two parameters. So, this is one of such example that how the choking velocity can be predicted. There are several correlations available, and that can be taken from the literature. So, this choking velocity, once again we have to avoid and we have to operate above this velocity. Now, similar to the vertical arrangement, in the horizontal transport we can have saltation velocity, Now here at a very high velocity, this is the superficial gas velocity and this is y axis is the pressure gradient. Now in this case again at a very high velocity, we can see that the pipeline cross section is uniformly distributed with the solid particles, which is we can say the concentration is lower, so that this is the dilute phase transport. Now if there is no particles in the pipe, it would be giving this kind of a result, the superficial velocity and the pressure drop line. But once it is introduced, the solid particles are put into that system, or it is conveying the solid particles, this kind of graph would be resulting, which shows that as we decrease the velocity from the dilute phase transport, it would, similar to the choking velocity, would reach a critical velocity in the horizontal transport, where the saltation of the solid particles would take place. What is that we have seen in the slurry transport? It is analogous to that, and that velocity is called the saltation velocity. In this case, the pressure drop requirements rapidly increases, and after that if we further decrease the superficial gas velocity, the result would be that there will be a clear separation of the settled solid, which will partially block the channel or the pipe, and there will be a small section or the area through which the gas will be passing through. Some of the solids will be carried with that gas phase or the air, and then also the pressure drop requirement will be further higher. So in case of horizontal transport, this saltation velocity is what demarks between the dense phase flow and the dilute phase flow. In case of choking velocity or the vertical transport, choking velocity is what defines or demarcates between the dilute phase transport and the dense phase transport. Now similar to this choking velocity calculation in the vertical transport, there are several correlations for the saltation velocity. Now in the saltation velocity case, as we have seen in the case of choking velocity, if we increase the solids concentration further, the saltation velocity also increases from G1 to G2, that means G2 is greater than G1. So the mass flux of the solids, if it is increased, the pressure drop increases, as well as the choking velocity or the saltation velocity in the case of horizontal transport also increases. So in this case also we can arrive at the saltation velocity for a particular superficial gas velocity by increasing the solids concentration, or for a particular solids concentration, if we decrease the velocity, superficial gas velocity, we can arrive the choking the saltation velocity in this case. Now similar to the choking velocity calculations, in saltation velocity also can be calculated from several correlations. There is no such theoretical development on this, but these empirical correlations helps in calculating the saltation velocity in the horizontal transport. Now one of such example or the correlation is presented here, and this is possibly the simplest kind that is shown here. Otherwise in the other correlations there are several parameters or several complexities or complex relations is involved, where this quantity is called the solids loading, which is defined as the mass flow rate of solids to the mass flow rate of gas. And this parameter or this quantity we call the Froude number. Where x is the diameter of the particle, g is the diameter, d is the diameter of the pipe, g is the gravitational constant, rho f is the density of the fluid, u salt is the saltation velocity. So, what we have seen today, the introduction to pneumatic conveying, two different zones or two different extreme of this transport condition, that is the dilute phase transport and the dense phase transport. What are the characteristics of these two? In case of dilute phase transport, horizontal as well as the vertical flow, how do we arrive at the choking velocity and the saltation velocity? Choking velocity in case of vertical flow, saltation velocity in case of horizontal flow. So, when we will further mention about choking, that would imply that the orientation of the pipe is in vertical direction, and when we talk about saltation, it means it is in the horizontal direction. So, these two velocities, how to calculate them, how to determine them, this we have seen in today's lecture. We will continue this discussion and we will see you in the next class. Thank you for your attention.